Thank you very much. And I would like to thank the organizers for giving me the opportunity to present my work here. So a sort of very broad overview of what I'm going to talk about is if you take a sub-Riemannian manifold, then you can make a sense of a notion of like random bridge processes. The idea being you have a fixed starting point where you start at time 0. You have another point where you want to be at some fixed time, like say capital T. Then you have like some random evolution from the starting point to the end point. And then this is a bridge process. And these things you may want to study. And actually they can be quite interesting from various perspectives. For instance, these bridge processes can be linked to small-time heat kernel asymptotics. They also do encode some information about the geometry of the space. And then there are actually some more sort of applied motivations of why you may care about these bridge processes. And now, when I first started off studying such processes from a like very theoretical level, I thought, well, it would be a nice idea to sort of get a better intuition of what these processes do. So how about we simulate them? But then it turns out that back when I thought about this, like basically none of the existing simulation schemes applied to sub-Riemannian diffusion processes, basically because the very first assumption was always that a certain matrix was invertible, which if you were in the true sub-Riemannian setting was just not the case. So now finally in joint work with Erlend Grong from the University of Bergen and Stefan Sommer from the University of Copenhagen, we're actually able to efficiently simulate bridge processes in that setting using some tools from machine learning. But before I get there, I just want to give you a better idea of what these bridge processes are, which we care about. So the setting we start off with is a sub-Riemannian manifold. So we have our underlying manifold, and for this work we actually do assume that the distribution in our sub-Riemannian manifold has constant rank. So throughout we have this assumption that the rank of the distribution is constant to some k, and we assume that we have like a true sort of true distribution in our tangent space. And now if we have our sub-Riemannian manifold, and then additionally endow the sub-Riemannian manifold with a smooth measure, then we can make sense of this notion of a sub-Laplacian, which is sort of just as close as you can get to the usual Laplace-Beltrami operator in the sub-Riemannian setting. Once we have our distribution, we can make sense of the horizontal gradient, and then the moment we endow the entire space with a measure, we have the divergence available as well, and then our sub-Laplacian is simply the divergence of the horizontal gradient. And if you do have an orthonormal frame, maybe local, available for your distribution, then you can actually write down an expression for the sub-Laplacian explicitly. And the thing I want you to notice is that a change of measure only changes the first order term. So the higher order term is always going to be the square of our vector fields, which give you the local orthonormal frame. And now what we care about is, first of all, just a simple diffusion process on this manifold. So what happens, we have this manifold M. We fix a point on this manifold, x0, is going to be throughout our starting point for the diffusion process. And then we have some random behavior, and this random behavior is determined by a so-called infinitesimal generator, which throughout we denote with 1/2 L, where this is simply 1/2 of the sub-Laplacian plus potentially a smooth vector field. And do notice in here that because the measure only affects the sort of linear term, if we have the freedom in choosing whatever smooth vector field Z we want, then this basically compensates the short choice of measure. So instead of choosing choosing the measure, we have now our choice of smooth vector field Z coming in. And then the only other thing I want to say is this sort of 1/2 is kind of the common convention if you deal in stochastic analysis. Obviously, a priori, there's no need to have it there. Just in other settings, it then kills a lot of factors of 2. So that's why it's more convenient to just put it into the generator. And the idea is that this infinitesimal generator gives you like an idea of how the particle moves infinitesimally. The Z is sort of a drift behavior, and then the 1/2 of the sub-Laplacian is sort of how this particle fluctuates around. And now this diffusion process comes with its heat kernel in a way, which sort of tells you a lot of how this process evolves. So we denote PTY. Basically, if we start all our mass at x0, at time 0, then how much of this mass has evolved to like nearby point y, infinitesimally nearby at time t. So that's what PTY denotes. And then I write it down here because this is a very convenient property. Basically, to understand how much mass has arrived to y by time t, equivalently, you can rephrase that, okay, in time s, I go from anywhere, I go from a starting point x0 to anywhere on the manifold, and then I need to go from anywhere to the point I want to be at time y in the time frame from s to t. So this is why you have this integration, how you can split this heat kernel. And one further property we have available in our setting is that because our generator for the stochastic process is so-called time homogeneous, meaning in this particular case, because it just had no dependence on time, it only had dependence on like the space, we do have the nice property that sort of the probability of going from x to y, where we start at x at time s and started y, or want to end up at y in time t, is sort of the same thing as going from x to y in time t minus s. So there is this sort of nice homogeneity as well for these heat kernels. And now, using these heat kernel, one can actually write down the generator of the associated diffusion bridge. So what is the idea? Is we had this stochastic evolution, and now we also fix a point x t, and we want to guarantee that our stochastic process ends up at xt at some positive capital time t. And by a sort of change of measure argument, you can write down the generator for this bridge process. And the one thing I want you to maybe get a bit familiar with is this sort of additional term. So basically, like the diffusivity of your bridge process, how it sort of fluctuates around on very small scales, is still going to be dominated by this sub-Laplacian. But the one thing which changes is that we now have this sort of additional drift term. And for instance, if you were to compute this explicitly in the Euclidean case, so in the Euclidean case, the sort of canonical stochastic process you have is the so-called Brownian motion, and then your heat kernel will be given by Gaussians. And there you can actually compute explicitly that this sort of gradient of the log of the heat kernel gives you an expression of xt minus wherever you are at the moment, divided through by capital T minus t. Now, if you look at this expression, basically what it does is that if you're close with your lowercase t to your final time, capital T, but spatially you're still very far away from where you want to end up, this is going to become very large and sort of pointing you exactly in the direction you want to end up. So basically, on a sort of grand scheme of things, this additional drift term makes sure to pushes you to exactly the point where you want to end up at capital T. And one can basically check that then with probability 1, all of these processes will indeed end up at xt at time capital T. And one more thing I want to highlight while we're here. So later on, what I'm basically going to argue is that there's a way to train a neural network to learn this log gradient of the heat kernel. And now, at some point you may wonder, why are we doing the steps we're about to do next? Why couldn't we just train a neural network here and then save us the pain which is about to happen on the next few slides? Well, do appreciate here that kind of the variable we want to put in is in the first component. So if we just were to try and train something here, it's kind of we have to like change our starting point and check how likely it is that we end up at the end point. So this will be sort of, would require a lot more samples than what we are going to do. I just want to remark that there's one special case where you could kind of make your life slightly easier. So in the situation where your additional vector field Z is actually divergence free, what you can do is you can look at the stochastic process whose generator is simply the dual of your original generator. And if you do that, you end up with heat kernels where the components are just swapped around. And then in that particular case, what you can do instead of what we're about to do, you could just like basically swap over your components and then do the training with respect to a different stochastic process. But I want to highlight that in general, we don't have that assumption. So that's why it would be nice to have something which works more generally. Okay, so what one can show is the following. And so far, what we've done is we started at x0 at time 0, and we wanted to end up at xt at time capital T. And what we care about is sort of simulating path of this random process. Now, on the pictorial level, it doesn't matter if instead we start off at xt, sort of at time 0, and work our way backwards to x0, provided they sort of follow the same random law in doing so. And now there's a notion of sort of time reversing a stochastic process, which is exactly just this definition up here. So the process at time lowercase t is just the original process, bridge process evaluated at capital T minus lowercase t. And for that one, you can actually also work out the generator quite nicely and noticeably. So this pt is still the heat kernel associated to your original stochastic process, so the one who sort of starts at x0 and moves forward. But then this is the generator for this bridge process, but where we start at xt and work our way back. And what I want you to appreciate is now we have a swap of the components. So basically, now it'll be enough to simulate a lot of paths for the original process, which start at x0 and then sort of explore the entire space. And maybe to give some idea of where this comes from, so I'm not going to write down the full details of the proof, but actually the proof is relatively straightforward. So this was the term we had if we just looked at the bridge process evolving forwards. And this Q is basically the heat kernel associated to the bridge process. In a way you can think of it, if the bridge process wants to be at y, at capital time t minus t, we first have to go from x0 to y in this time t minus t. Then we have to go from y to the endpoint in the remaining time, and then we have to sort of divide through by all the mass where you actually go from x0 to xt. And then it basically turns out if you take the log gradient of this, which is a term you obtain when you reverse the process, because if you reverse the process, you get another drift which ensures you really end up at the starting point you want to end up with, then they just cancel in a very nice way, and you end up with this log gradient. And then rephrased slightly, well, it's the same theorem, just rephrased slightly. So now in sort of machine learning, there's a notion of a score. And the score is simply, I'll write it down for future reference. It is exactly this log derivative of the gradient. So this, the log derivative of the heat kernel. So this is simply this expression. Where this indicates that we're taking the derivative with respect to the second component. So just keep that in mind. We do make the convention that if we don't specify the starting point, we think of x0, but at points we will have to specify the starting point. And then with that, the theorem can be just expressed as follows, that we now have sort of the generator for the time reverse process, bridge process, is 1/2 of the sub-Laplacian minus the drift term, because just think if we sort of have drift that way, if we move forwards in time, then if we move backwards in time, you sort of have minus of it as a drift. And then we have this score appearing, which is the gradient of the log of the heat kernel. So what the aim is going to be is to simulate our bridge processes. We simulate the sample path by going backwards. So we start from xt, going back to x0. And the one ingredient we still need is we somehow need to get access to the score. And to be able to learn the score, what we will do is we essentially will simulate a lot of paths from the unconditioned process forward. From x0. So that's just something I want you to appreciate. We simulate the bridge process sample path backwards, but then to be able to do that, we will have to simulate a lot of the original process path forward. Okay, so that's sort of the idea of the bridge processes. But now the sort of one catch comes in is that, well, I've written down what happens if we're in the Euclidean case. This sort of log gradient looks very nice. But in general, this score we basically don't have an explicit access to. So this is usually very intractable. There are a few cases where you can still write it down explicitly, but usually it's like, okay, how do we even get access to this? And this is where basically the full power of machine learning and neural networks comes in. So what we want to do eventually is we want to be able to obtain a very good approximation for this score. And to be able to do that, one thing, well, we assume is because we have the constant rank assumption, we just take a frame, local frame for our distribution, and then at some point we basically want to learn these kind of functions which are simply the coefficients for our frame. And what the notation here is that basically S is going to be our true score. So this is a time-dependent vector field, because here we have the time dependence, and then if we evaluate it at a point, we get out a vector. So it's a time-dependent vector field. And then these S thetas are going to be approximations to the score, where the theta is sort of like one letter which denotes all the possible parameters we have. So this is basically a family of parameters which we can tune, and we need to find a way of how to tune it. So we need to find a way of saying, okay, so what is a good approximation to the score? What is a bad approximation to the score? And throughout what we're going to do, we want to work with the sort of squared L2 distance. So this here was our true score. This st theta is meant to be an approximation of the score. So to judge if this approximation is any good, take this difference, provided we are sort of made sure that we can do that, then because we are in our distribution, we can determine its norm with respect to our sub-Riemannian metric, take its square, and then just integrate it over the entire space and over the entire time. And to make the notation slightly nicer, basically the second line is only a different way of writing down the first line. It's simply we have an integration with respect to the heat kernel. So the shorthand notation is by simply saying this is the expectation. We have the x0 here still because we still care about x0 being our starting point. And then it's basically just the approximated score minus the true score as our error. So this by itself is not going to be particularly helpful because the whole point is we don't know the true score. So that's why if we have an approximation, we cannot say how close it is to the true score, which we do not know. But it turns out after a few tricks, we're actually going to be able to say something about it. So one observation, which is going to be helpful later on, is that, or maybe briefly go back. So if you look at this expression, we have the square appearing in here. So there are a number of terms. If you sort of expand it, we have the norm of st theta squared. Then we get an inner product as well of st theta and the true score. And then we also get the norm of the true score squared. And now, one thing when you sort of look at these things term by term, you can check that this expression doesn't depend on s at the end of the day. So this may look a bit magic at the beginning, but it's also just a few lines to prove that. And basically what you use in this proof is something I said right at the beginning, that if you want to go from x0 to y in time t, you can first go in time s to anywhere on your manifold, and then you have to go from that to y in the remaining time. If you use that, basically this identity just falls out. That's all what it uses. So this is something interesting to notice, that this inner product, which appears in our loss function, will actually be able to play around with this s. And then in this particular case, it's important that we change our starting point in this score definition. Okay. Then the next observation, well, first of all, we now introduce this est theta, and I'm also going to write this down because we will need that a few times. So what's happening in here, so again, we take the expectation where all our paths start at x0. Then we first basically have the norm of the approximated score appearing. And then we have this second term, which we just introduced. So we end up with that expression. We'll encounter it a few times. That's why it's helpful to have it up. And the first thing you observe is that the thing we take the time integral of, and our loss function minus these est thetas, they actually are constant with respect to theta. It's not that hard to see because basically this part in here kills the dependence if we have the norm of the st theta squared. then the next dependence is killed using this identity, and then you only have the square of the true score left, but this is sort of always there, and notably it doesn't depend on theta. So that's why if you can minimize the one thing, then it's still going to be a good minimizer for the other thing. And what this already means is that if we want to get, or if we want to minimize our original loss function, we can rewrite this slightly, which for now looks like it's not going to be helpful, but actually later on it will be helpful. So we have these following two ways of rewriting our loss function. So this curly E theta was our original loss function. Then by the argument which we just had, we can write it as follows, where curly E t theta is just the integral from 0 to t of this little e st, which we defined. And then I'll write it up now because it's going to be helpful in a moment. You can also add up a lot of these things for partitions of your time interval 0 to capital T, where eventually we care about these ti and ti plus 1 to be quite near each other. Okay, so now this by itself, as I said, still looks like it's not going to be particularly helpful because these curly E, st or 0t still depend on the true score. But now the very nice thing happens is that if you take this and literally the only thing you do is you, well, apply the definition of the divergence or the divergence theorem, depending on how you call it, to pull the gradient to the other side and turn into a divergence, you end up with an equivalent expression for this of this form. So basically there's a flip of sign compared to here just from applying the definition of the divergence. And notably, all of a sudden, this entire thing only depends on the approximated score. So by doing this trick with applying the definition of the divergence, we lost the entire dependence on the true score. So now we're in business because this whole thing only depends on our approximated score. And then we can compute this thing, and we can now minimize with respect to that to obtain a good approximation for our true score. So this is just what I just said. We can use this sort of equivalent loss function to obtain a helpful loss function to compute our score. And then just to put this down, obviously, if you see this expression for the first time, numerically, there are still a few things you can't really deal with. So what you want to do is, well, first of all, there are basically two integrals you have to deal with. First of all, you have a time integral because we still take the time integral of these things, but you just do your usual thing. You sort of partition your time interval and do the sort of summing up and dividing through by the length of the time intervals. And then your expectation at the end of the day is also just an integral. And to approximate that, what you do is there fairly cheaply you can generate a lot of samples from your original unconditioned process. So that was the sort of path I indicated in red, where you just have your true original process starting at x0. It's relatively efficient to generate a lot of those paths, and then you can compute this sum for relatively large k, and then this gives you a decent approximation of this loss function. Okay, so, and maybe just to put that out, that's sort of how the algorithm, or like the pseudocode, would look like. You have your input, which is like your initial point, the point where you want to end up. Then your sub-Riemannian structure, which is fed into you with the vector fields. Then a few things you do need for the learning. And then what I said, you can sample a lot of these sample paths for your original unconditioned process. You compute the loss function using the sum or the double sum, which was on the previous slide. And then you sort of do like a gradient descent that you just want to make your parameters more efficient. So that's the rough pseudocode. And basically, if everything was nice, we'd be done at that point. But there are a few problems with that loss functions. The first one is that we have this divergence of the loss function appearing. We have the divergence of the approximated score appearing. And that, because we only deal with sort of finite sample points, can lead to unstable convergence because it ends up being we sort of maximize or optimize things at our sample points, and then that doesn't necessarily give you a particularly stable convergence. So that's one problem. The next problem is that if the dimension of your manifold is relatively high, then finding sort of suitable derivatives of your neural network, which we need to deal with this divergent terms, and then also taking the gradients, which we had in our optimization of the weights, can become sort of extremely expensive to compute. So that's the second downside. But then actually, exactly the same problems have occurred in the Euclidean setting. So this isn't necessarily a problem which only is there because we work in the sub-Riemannian case. It's really, it's already been there. So the nice thing is people have already thought about it. So there's a so-called approach by denoising loss with like sort of original works by Habermann and Vincent. And what their thought was, well, instead of getting like a really nice expression where we only express our loss function in terms of the approximated score, at some point we need to approximate things anyway. For instance, in our loss function, we then had the, when we were approximating the approximation and the time integral, there were already additional errors coming in. So their thought was, well, if I go back to my little est theta, then the reason why it depended on the true score was this approximation. But now look at how the true score was defined. So we have this t then replaced by t minus s. So we have the log of the heat kernel appearing. And if t and minus s is very small, then we kind of have an idea of what the heat kernel does. So for instance, if we are like in a sort of Euclidean case, then for t minus s, very small, like your steps sort of look Gaussian-like. So you have a rough idea of what's going to happen, which is been very successful, and people have then used this kind of approximation in the Euclidean setting to obtain good approximation for bridge processes. And there's now one additional sort of complication coming in if you work in the sub-Riemannian setting. So if you think like, okay, so now in the sub-Riemannian setting, I can't go everywhere in space. That shouldn't necessarily stop you at the beginning. Well, you have your sort of starting point, and then tangentially, you can sort of go in a certain number of directions. So let's try and do like a Gaussian in that space. So that by itself can be made to work. But then the catch comes in at this point where you take the gradient with respect to the second component. Because your frame basically starts to twist, so your sort of approximation to the Gaussian will live in some subspace. And then you basically want to take the gradient. So this is sort of where you start off. This is your sort of approximation of what your heat kernel does on very small level. But then you want to take the gradient once you're here. And then you sort of like, because of the twisting of your frame, the question is, okay, how exactly to take the gradients of that? in our work, we have managed to find one way of doing that by sort of assuming if the distribution doesn't twist too much, then it shouldn't make that much of a difference in sort of just taking the gradient in the space where you can actually take the gradient. So that's one a way of dealing with it. And then the sort of slightly more optimal way is, well, even though we're on a sub-Riemannian manifold, we do by now have a fairly good idea of how small-time heat kernel asymptotics look like. So these kind of Varadon-like asymptotics, where we know that suitably rescaled, the log of the heat kernel will converge to minus the Kano-Kara-Theodori distance squared between the 2 points where we compute our heat kernel. So then the question is, we can try and use that as an approximation, or in an approximation for a potential score. But additional problems which come in here is that obviously, so how do we gain access to the Kano-Kara-Theodori distance? But keep in mind, we don't actually have to compute it explicitly, we just need to have a good enough approximation. And then one thing you could do is we can work in adapted coordinates. So we care about our point x0, which is our starting point. And then we take adapted coordinates which are centered at x0, which have weights attached to them. So for instance, if you work in the first Heisenberg groups, your weights are like 1, 1, 2. And then you have, you can write down this d hat distance, which actually is Lipschitz equivalent to your Kano-Kara-Theodori distance, so sort of not too far away from it. And then what we can use as an approximation for the score is just we take the log gradient of this d hat instead, and then we need to respect the scaling which we needed for our small time asymptotics to actually recover the thing. And then for the Heisenberg group, this can be computed explicitly. So up here, we had a certain freedom of these constants. So basically, for whatever positive constants you choose, you do get Lipschitz equivalence metrics, and there's a bit of a question, how do you choose these constants? What we've done on the Heisenberg group was just to choose the constants in a way so that the metrics actually, the distances actually coincided on the axes. So it was chosen so that if you walk along the, away from the origin on the x-axis, you get the same thing on the y-axis and then on the z-axis. This is the reason basically why there's a pi appearing at some point, because that appears in your distance along the z-axis. And then one more thing I should say is, why is this S suddenly in bold? Well, the idea was if you take your frame for your distribution, then these things are just the coefficients in front of your frame. So kind of the first components, so this is actually true in all Heisenberg groups. So if it's just the first Heisenberg group, then sort of this is the coefficient for the first vector field, and then the second line is going to be the coefficients for the second vector field. But actually, it works more broadly. If you work in like 2n plus 1, then x is going to be a vector in Rn, and then this is your sort of coefficient, or these form your coefficient for your first n vector fields, and then down here you get your coefficients for the second lot of n vector fields. Okay, and then with these things, we can actually successfully simulate diffusion bridge processes. But before I show you pictures of these diffusion bridge processes, so basically the whole machine learning comes into the game where we have to learn the score. And the score was this sort of log derivative of the gradient. And this is if you start off using this divergence loss, where z sort of theoretically is very nice because it's a true approximation, or like it's a correct loss function which tells you of how good your approximation is to your true score. But there were the remarks that it's sort of an unstable convergence, and basically this is why here sort of you have some errors appearing, which are not that nice. But something which I particularly like about these approximations is that, so we go back to the Euclidean setting, the idea of the bridge was that it pushes you to where you want to end up. And for the Heisenberg group, we know that our geodesics are helices. And essentially, if you stare at the picture for long enough, you kind of see that this is also what the score does. So what we will care in the end is we care about a bridge from like 0 to somewhere. So to do that, we start at somewhere and want to push back the particle to 0. And the way this whole thing is twisted, it's basically going to push you along the correct helix, which ends up at the origin at the desired time. So you kind of do see, without us ever having input any information on the geodesics of this space, you see how the score picks up on this. It sees the geometry of the space to some extent. And then in here, this is the approximation where we use the denoising loss, where we use these adapted coordinates to get an approximation for the small times. And that was the reason why I've written down the second approximation, because we then know what the score does for these things very small. So we just have to do it a lot of times, sum these things up. And then you notice that here you don't have the outliers as you go far away. And again, you see how this space kind of in a way learns the underlying geometry, or how this score field learns the underlying geometry of the space. And then here is a simulation of a bridge. So the idea is you start off at this point, which is 0.5, 0, 0.8, and it's pushed back to the origin. Then in this plot, the blue curve is the z component of this bridge process. So you see how it dies down to 0. This is the norm in the xy plane. So obviously, because we have this helix-like structure, it has to go further away from the origin for a while to then go down. And then something else to notice. So this point was chosen, so we specifically didn't choose it on the z-axis. We moved it slightly away because this is a point where we actually have a unique geodesic in the Heisenberg group joining the 2 points. And now there's a work by Bergen and generalise, which is if, like on any sub-Riemannian manifold, if you have 2 points which are joined by a unique minimizer, that minimizer may be abnormal or not, but it has to be unique, then you know that in small time, your diffusion bridge process will actually get close to this minimal path. So basically, if you allow the particles less and less time to go from the starting point to the end point, then it will stay very close to this minimizing path. And in here, you at least see that qualitatively, this is what the diffusion process is aiming to do. So we do give it like 0.5 time to do that, but on a qualitative level, it does stay fairly close to this minimizer. And I should also point out, obviously, smaller time frames at some point do get more complicated for simulations because things just start breaking down if you want to move on a very small time level from your starting point to your end point. So this is sort of the best you can do to demonstrate that we actually do stay relatively close to the minimizer. And then something else sort of which goes in the same regime, actually the work by Erlend Grong, they also study fluctuations around minimal path. And now what's happening in these pictures is basically down here, we give the bridge process time 1 to make it from the start point to the end point. Here it's 0.5, 0.2, and 0.1. And you really see how things start to localize near sort of the mean path. So again, this is sort of an indicator that qualitatively these approximations really do the right thing. And then what I just want to point out, all of the code is actually available on GitHub if you do want to play around with it yourself. I should just put down the details. Obviously, we do use neural networks, as I said, and we are quite explicit exactly on what structure we use for the neural networks. But yeah, if you follow the links, you will find the code available to play with. And that's actually where I'm going to stop. Thank you very much.